Okay, so we're starting into Chapter 5 now, and most of Chapter 5 is about constructions. And constructions are just ways of creating geometric figures using nothing but a straight edge and a compass. And we'll get into that a lot in class. It's one of those things that needs to be a lot of hands-on type of stuff. And so we'll do that in class. All along the way, we'll pick up some different theorems as well, and some different ideas that allow us to use a straight edge and compass to make all of these guys. A lot of these theorems are the basis behind using a straight edge and compass to make our geometric figures. So the purpose of today is to talk about mid-segments and then talk about coordinate proofs. You should be able to use the idea of mid-segments to find different lengths and then be able to write out a coordinate proof. They're a little bit different than two-column proofs. Oh, sorry, here. All right, so first things first, a mid-segment. A mid-segment of a triangle is a segment that connects the midpoints of two sides of a triangle. So in this first picture in your notes here, you're going to know that you're looking at a mid-segment because we'll draw a segment through a triangle, and then we'll show that the mid-segment hits the midpoint here. So point E would be the midpoint of BC, and we know it's a midpoint because it's breaking BC up into two congruent segments, BE and EC. And we'll know that this segment hits at D, and D is a midpoint for AB because we'll have these tick marks to show us that AD and DB are congruent. Okay? And so that's what a mid-segment is. Because of the position of the mid-segment, so here DE is the mid-segment of triangle ABC. Because of the position of the mid-segment, the segment connecting the midpoints, or the mid-segment, of two sides of a triangle is automatically parallel to the third side. Not only is it parallel to the third side, but it's also half as long as that side. And this is the mid-segment theorem. So you'll know two things when you hear the word mid-segment, or if you see a mid-segment. One, you'll know that the mid-segment is parallel to this third side, and it's also half the length, right? So we'll know that DE and AC are parallel, and we'll know that DE is half the length of AC. Okay? And so we can use this idea. So this is example is not necessarily in your notes, but we'll take a look at it anyway. It's pretty short and sweet here. Okay? As a matter of fact, it actually is in your notes. It's the example 2 there. So you can label the triangle the way it is here, where TU is X and PQ is 10. If that's the case, find X. Well, we know from the mid-segment theorem that the length of UT has to be half the length of PQ. And so since PQ is 10, UT gets to be 5. Okay? Not only that, but we know that UT and PQ are parallel. Now, I want to take a second to go back here, and since the word parallel has come up, we've got two parallel segments, and this guy can be viewed as a transversal, okay? And if it is, if you look at that as a transversal, remember we have angle relationships between parallel lines. We have corresponding angles that are going to be congruent, that's what those are, and we have consecutive interior angles that are going to be supplementary. Not only do we have that on that side, but we have it on this side as well. Corresponding angles, congruent. Consecutive angles, supplementary. Okay? Don't forget those relationships. We'll bring those back as well. Okay? All right. Now, next example in your notes gives you this triangle and some information. It says that ST and TU are mid-segments. And then we've got the length of PQ and the length of ST. We want to find PR and TU. Well, TU is the midsegment, and that's half the length of PQ. This is a lot like the last example there. So TU is going to be half of 10, and therefore 5. And then the same thing pertains to ST as well. ST is going to be half the length of PR. Now, ST is 8. So to find PR, we just multiply both sides by 2 or double it, double ST. And so we see that PR has to be 16. Okay? We might want to get in the habit of writing out these equations and just plugging in what you know. It might make things in the future a lot easier for you. Okay? All right. A quick application here. Construction, home construction in particular. Homes, the roofs, whatever the plural of roof is, it doesn't sound right. Anyway, are all made out of trusses. They're superstructures that are made out of trusses. And they're triangular in shape. Anytime you see a house being built, the trusses 99% of the time are triangular in shape. And they have these support beams all through them to help give them strength and form. Okay? Now, what we know about these trusses is that each of these segments here are perpendicular to this long wooden piece here, AG. And the support beams here are placed so that they create these congruent segments here and these congruent segments here. Okay? That being the case, if AG is 24 feet, AJ and GJ are 15 feet, and HB is 3, as well as LF being 3. We can determine some lengths here. The length of CD. Well, you see that CD is congruent to all these other guys here. There's 1, 2, 3, 4, 5, 6 congruent pieces that all make up that 24 feet. Since they're all the same and they have to add up to 24, we can just take 24 and divide it by 6 and get 4. So each of these guys, including CD, are all 4 feet. CI. CI is right here. CI is in this triangle where HB is apparently a midsegment, and we know that because these two segments are congruent, these two segments are congruent, which tells us that H and B are midpoints. Now, since HB is a midsegment, CI is 2 times the length of HB. In other words, it's 2 times 3. In other words, it's 6 feet long. Now, in this picture, can we conclude that HB, IC, JD, KE, and LF are all parallel to one another? And I think the idea is to use the mid-segments, but we already know that these guys are all perpendicular to the same line here. So that makes them parallel to each other as well. We had one of those parallel line theorems that said that if two lines are perpendicular to the same line, they have to be parallel, and that's true all the way across here. Okay? Another little application of mid-segments and the parallel line theorem. Okay? Now, next idea before we get to our constructions is a coordinate proof. A coordinate proof is different than a two-column proof in its structure. A coordinate proof involves taking the geometric figure and putting it in the coordinate plane. We let variables represent the coordinates, any of the coordinates that we don't know for the figure. If we do that and we generalize things down to variables, then we can say the results are true for all figures of that type. Now, we've done things kind of like this, but we actually gave the vertices numerical coordinates, which means the only things that we did before was prove things for a specific shape. A coordinate proof allows us to show something is true for all versions of that particular shape, not just one. Okay? Now, the idea behind a coordinate proof is that we want to place the shape in the coordinate plane strategically, because we can put the shape anywhere we want to. For example, if we want to place an isosceles triangle in the coordinate plane, we want to do so that it's convenient for us and convenient in finding side lengths. And then we're going to assign coordinates to each of the vertex. Now, what do you mean by convenient for finding side lengths? Well, remember that when we're in a coordinate plane and we want to find the length of segments is the same thing as the distance between two endpoints. So we're going to use the distance formula wherever is necessary. But if you are looking at horizontal and vertical segments, then the distances are, to find those distances, it's simple enough to just use the ruler postulate, which means that we just count lines basically, or subtract x values or subtract y values, and I'll show you what I'm talking about in just a second. Okay? Now, the other thing that's going to make life easier for us is if we put one of our vertices at the origin, at 0, 0. Because that way we know what that coordinate is, and since the coordinates are zeros, the math ends up being much, much easier. So let's take a look at an example. Let's say that we put this triangle in the coordinate plane, and we do so that one vertex is at 0, 0, one vertex is at 2m, 0, and one vertex is at m, m. Now notice we're not using numerical values, we're using variables. And the idea behind that, we're using variables, and the idea behind that is so that we can generalize this to any triangle of this particular shape. Okay? Here's what we want to know. We want to prove that this is a right isosceles triangle. Okay? How do we show that? Well, you see here that this suggests the coordinates of the vertex angle as being m, m makes both legs congruent. Well, how do we know that? We'd have to show that, right? So in other words, we'd have to go find the length of each of these sides. The length of this side, the length of this side, and the length of this side. Well, here's what we mean by strategically placing these things. This side was strategically placed to be a horizontal segment. Now, we can use the distance formula between these 2 points if we want to. But since it's a horizontal segment, it's simple enough to use the ruler postulate, which means that since the y values don't change, all we have to do is take the absolute value of subtracting the x's. So, 2m minus 0. When we do that, the length of this side is just going to be 2m. And hopefully that's easy enough to see. Okay? Now, we need the other two distances to see if we have two congruent sides. So I'm going to do D1 and D2. Now, D1 is the square root of, and now we're going to subtract the x's. X, y, and x, y. So we go m minus 0 squared plus m minus 0 squared, which gets us to the square root of m squared plus m squared, which is simply the square root of 2m squared. So that's D1. Now D2. Now obviously the square root of 2m squared is not the same thing as 2m, so those two sides are not congruent. Let's go find this other distance and see if we have two congruent sides. So now I'm going to use it for this x and y. So now I'm going to do it for this point and this point. So subtract the x's. 2m minus m squared plus 0 minus m squared. Okay. Now, 2m minus m is m squared. 0 minus m is negative m squared, but when you square negative m, you just get m squared. And so we get the square root of 2m squared. Now, these two are the same. So we do have an isosceles triangle. These two sides are going to be your congruent sides. Okay, those are your legs, and this guy down here is your base. Okay, now, is this a right isosceles triangle? Is one of these angles going to be a right angle? And there's a way to check. It's really the only angle measure that we're able to determine in a coordinate plane, because what we can do is we can find slopes of sides. And remember that that right angles are formed by perpendicular lines, and perpendicular lines have opposite reciprocal slopes. So all we've got to do now is go find the slope for each of for a couple of sides. Now we can eliminate having to find the slope of this side, because if these two sides are your legs, then these opposite angles are the base angles, and base angles are congruent. If those two angles are congruent, no way can they both be 90 degrees. So the only angle that can be your right angle has to be that guy, the vertex angle. So that's the only angle we have to worry about, which means now I got to check to see if this side and this side are perpendicular. Those are the two sides that I want to find the slope of. Okay? Now, I'm going to get rid of this work because I've already shown that those two legs are congruent. Obviously, if I had enough room in a true proof, I wouldn't be erasing this work. You'd want to include that. But now I'm going to find the slope, and I'm still going to call this side D1. Forget the notation. But I just need the slope of this side D1. Okay? Well, the slope is the change in y over the change in x. In other words, subtract the y's over subtract the x's. Well, the y's between these 2 points are m and 0, and the x's are m and 0, so we get m over m, or just 1. Now I've got to go find the slope of D2. Same thing, subtract the y's, so I go 0 minus m in the 2 points I'm using here, in case it's hard to follow. Now I'm going to use for D2, I've got to use these 2 points. So 0 minus m over 2m minus m. 0 minus m is negative m, 2m minus m is positive m, and when you divide those out, you get negative 1. Remember, perpendicular slopes are opposite reciprocals. So if I take negative 1 over 1, I have to flip it and switch it and be able to get to the other slope. If I flip this, I get 1 over negative 1, switch the sign, we just get positive 1. These guys are perpendicular, so these two sides are going to form a right angle, and so that vertex angle is a right angle, and we have a right isosceles triangle. Okay? So our coordinate proof looks something like that. All right. That gets us to our constructions. This is the end of the video. Like I said, the constructions we'll do in class because it's so hands-on. Okay? See you guys next time.